Yeah, thank you for inviting me. I'm very pleased to give this talk, and we've been working on this thing for several months with Pink. As we were talking about, it was very hard to find a slot which works for these different time zones. So I'm going to talk about learning with less labels, and the this whole revolution of deep learning started with supervised learning. And supervised learning, as we know, that requires large label sets, and which is very hard to get these annotations because it's expensive, it's time consuming. So then to deal with that, one approach is semi-supervised learning. And there we have the some label data set and lots of large number of unlabeled data. So that has been working out pretty well. So there are two main dominating approaches. One is the consistency regularization, other is a pseudo label. Then another approach to deal with annotation is a few shot learning. So here the idea is that we will train a model on a set of base classes, and then we will adapt the model to novel classes with only few samples. Okay, so here the number of annotations very small compared to semi-supervised learning. Now it's of course challenging because we have limited data, limited annotations. So then the third level is self-supervised learning, and where we will train a model on a set of completely unlabeled data. Okay, so that's most challenging. And here we imply the p-test task, and then we will fine tune on a downstream supervised task. Okay, so I'm going to cover these three main streams. So I'll start first talking about the semi-supervised learning, which we call the UPS, and this was a paper in iClear this year. And then I will move on to few shot learning, and here we are going to use the invariance and equivariance jointly to solve this few shot learning problem. And this was a paper in CVPR last month. And then I will end with the self-supervised learning, in particular self-supervised learning for videos. We call it temporal contrasted learning or video representation, or tickler. Okay, so let's get started with the first one. So this is a paper with two of my graduate students, Rizvi and Kevin, and my colleague, Dr. Yogesh Rawat. And so, as I mentioned, there are two dominating approaches for self-supervised learning: consistency regularization. And here the main thing is that we use augmentation to get the invariant output distribution. And so this reliance on the domain-specific augmentation is a big issue. So it will only work where we have a possible augmentation, otherwise it's limited. Now, the way this works, that we have the label data and we train a simple network, F theta, using the supervised loss. And then we combine the labeled and unlabeled data, and then we have the augmentation of each sample, and we want to minimize the difference between them. So now pseudo-labeling is another approach, and it generates the pseudo-label for unlabeled samples, and it does not require any augmentation, and it performs poorly compared to consistency regularization method. So the way it works, that we have a label data, and we train on the supervised loss using the label data. Then we use that trained model to label the unlabeled data, and that's what we call pseudo labels. Now, once we have pseudo labels and the real labels, we combine and we train it again, and that is kind of pseudo labeling method for semi-supervised learning. Now, our objective in this work is that can we bridge the gap between the pseudo labeling and consistency regularization? Because as you know, that the consistency regularization methods have been very popular and they have been doing pretty well. So that's why we call this method in defense of pseudo labeling. So now we found out the fundamental issues with pseudo-labeling are that when we train with a small label set, it will lead to some errors in the pseudo-label generation. And these incorrect pseudo-labels leads to noisy training, okay? Now, so the main thing is that we need to remove those noisy label, incorrect pseudo-labels. And now simple way will be that we look at the confidence of the pseudo-label and we only use those. But now just using the high confidence pseudo-labels is insufficient. That's what we found out. And because these neural networks, they are not calibrated well, and they will give you the labels which have some problems. So that's why due to this, some incorrect super labels are still selected, and that creates a problem. So our approach, UPS, which is called uncertainty awareness pseudo-label selection, is going to select a subset of generated pseudo-labels such that the confidence is high. At the same time, network is certain about the output prediction. So that's where we are going to introduce uncertainty measure. So the pseudo-label selection, in a way, will be that we have this unlabeled data set, which is a big one. Then we can remove, we can select a subset of that based on confidence-based selection, but we want to select further subset of that based on uncertainty-based selection. Okay, so there'll be more better example which we can train on. So, so other point here is that now network can be confident that certain label, certain instances are not present in an image. Okay, certain classes are not present in an image. So this information we can actually use for negative pseudo labels. Okay, because if it says that it's certain that this label is not present in this class is not present in this image, then we can actually use this information, and we are going to leverage that. So the benefits will be that we will use a negative label learning for single label and classification. At the same time, this will be also useful for multi-level classification, because if particular class is not present, that doesn't mean that all other classes are not present. So that's the interesting point here. So which means, given this kind of the labeling, now if we know that these labels are not present, we can use this negative label learning to actually improve our network. So the UPS method, the way it works, that we have again the training on the label data set, which is shown here. So we have label and we use a cross entropy, and then we generate the pseudo labels. And simply it can be, if the confidence is high, we generate those. But then comes that we want to select the good pseudo labels. So that's where we will bring in addition to the confidence, we'll bring in uncertainty. Now it will happen that if we are confident, but if the uncertainty is low, then we are going to select. Otherwise, we are not going to select. So therefore, from this set, we know that these other example have the high uncertainty. So we are not select. We are going to only select these images, ship, bird, and kid. And then we can iterate, and that's the way our method works. So therefore, our generalized pseudo-labeling method is that we start with the label data set. So this is the image, and this is a label. And then we have unlabeled, we just have these samples. So we want to come up with the classification of each of the label, and this will say what ith label, which class is present. Now we want to learn this parameters model f theta such that we use this data set of the labeled and unlabeled. And of course, for the pseudo labels, we are going to use the pseudo labels for these data set, and for the label data set, we are going to use what labels they have. So, so we get this confidence PC for the ith image that this class is present, and then we are going to use these probabilities that we can generate the pseudo labels. So simple way will be that we can look at each of this class. If it's above some threshold, then we say that class is present in that sample. Now, this is more general. This will work also for multi-level classification. Now, a special case of this would be single level case, where there'll be only one class will be present. So we'll just book the maximum of all these probabilities, and that's the way people do in the single level classification. So now what we want to do for the selection, we want to come up with this function G, which will tell that which pseudo label we should assign for that particular instance I, and these are all possible classes. So the simple method will be that, well, if the confidence is high, then this is a positive label. If confidence is low, this is a negative label. Okay, so we can use this one. So if the probability score is high, then select the positive label. If network is confident that this particular class does not happen, then we'll select a negative label. And for positive, we'll use a cross entropy. For negative, we'll use the negative cross entropy. So now for the negative learning, for the negative class, single label, we are going to use a simple negative cross entropy. For the multi-label, we will use binary cross entropy, because each of the class can occur or not occur independently of the other classes. So then finally, just combining all this with the UPS model, where we have incorporated uncertainty. So this will be our selection. So we have two cases where we say uncertainty is low and the confidence is high. So this is a positive label. Here, if the uncertainty is low and the confidence is low, then this is a negative label. Okay, so that's our method. And this is our algorithm. So we start with the initial training of this network using the label data. We'll do several iterations of that, and we will generate a pseudo label using this model we just learned with the label data. And we are going to apply this confidence measure. Now we will select which pseudo labels which we should use. And the selection will be based on this selection function I discussed earlier. And then the selected unlabeled, we will add to the label, and this become the new data set now. And then we will train a new classifier in which we are going to use the cross entropy for positive and negative cross entropy for the negative, and which is shown here. And then we'll iterate, and that's the very simple method. So this works very well. And these are the error results on C410. We do the best, and these are the messages of consistency regularization with the sign, and the other one are the pseudo label, and this for 1000 label, this for 4000, and same phenomena for C400. Now, good thing about this method is that this, since it does not use augmentation, so it will work for any data set, every domain, like it works for actions also, because it's difficult to get the augmentation for the videos. Most of augmentation we know are for the images. And also it works for multi-label classifier, so which is like a Pascal, that each image can have, each image can have multiple classes, multiple objects present. So on the UCF 101, we get very good results compared to state of art, and also on the Pascal, we also beat the state of art, which is good. So we did the ablation study on this. So this is, if you use only supervised, there's an error. And then we use our method, but no selection, the simple pseudo labeling, we get this. And this is UPS, where we are using the selection, but you are not using the uncertainty. This is where we are using a simple MC dropout to do the uncertainty. This is when we don't use the negative labeling, and this is when we use the whole system. As you see that we have the lowest error for the 1000 and 4000. So also our methods not dependent on any particular method for the finding the uncertainty. It works for MC dropout, other special dropout, and so on. So that is also good. And also it's robust to the hyperparameters, as we talk about as this threshold of the uncertainty, and also for the confidence. And these are different values of that hyperparameter. As you see, the test error is pretty similar. So now these are the examples which were deleted using our method. So let me zoom in a little bit here. So like here, so this is an airplane. It has a very high confidence, this airplane, but the uncertainty is high. So therefore, these were deleted from our method. Okay. There's other example, I think here. If you look at this one, again, so this was a truck. So this was, deleted, this airplane, and so on. So that tells you that this method works pretty well. So this is available, code is available on this GitHub, and people are free to use it. So this was about the semi-supervised learning method using the uncertainty metric, and we kind of match the performance. We fill the gap between the consistency regularization method and pseudo-label method. That's why we call it in defense of pseudo-labeling, because that has been kind of inactive area. Most of the work is in the consistency regularization. So we wanted to bring back this topic here. So the next thing I'm going to talk about. Yes.
Can I ask a question here?
Yes, please, go ahead. Yeah.
Okay, so you apply negative learning to study the uncertainty of the predictions. Is my understanding correct?
No, the uncertainty is applied to everywhere, but the labels which are the negative, which are confidence are negative, that particular class not present, then we use that also to help improve. So these are uncertainty applied to all of them, the positive and negative also. Okay.
So my question is why negative learning can improve the performance of the whole scheme?
Mm-hmm. Yeah, because it provides additional information, right? So typically you will just use the positive learning, but here we are confident that particular class is not present because we are looking at the confidence and we are looking at uncertainty. It's very certain that it's not present. So therefore we want to use that additional information and typically ignore, and we show you that it really helps.
Okay, got it. Thank you.
Yeah, okay. So let's go to the next thing. And so here we are going to solve the few short problem, and we are going to use the invariant and the equivariance. So we know invariance in CNN. It provides better class discrimination. It's complex boundary, class boundary, and common examples of invariance in CNNs is that it is invariant to nuisance factors like natural perturbation, image transformations, and so on. So also equivariance in CNN, we are also aware of that it helps us learning better transferable features. Common example of equivariance are generalization of translation equivariance, translation, reflection, and rotation, any generalized transformations, and so on. So what we are going to do, we're going to combine those two strengths, and they kind of look, very different. One is saying that these transformation, the network should be invariant to that. Other is saying, well, if there is transformation, then we should be reflected in network. So which is kind of conflicting things, but we'll show you that if you combine these two, we can actually do much better. So, so this will give us better classification, class discrimination, and better transferable features. And this will be generic feature, which will improve generalization. And so we will enforce invariance and equivalence to set up geometric transformations. So any invariance and equivalence has to be with respect to some transformation, right? So, and this transformation can be similarity transformation, affine transformation. Now we are going to quantize the space of these geometric transformation for easy optimization, and we will solve this in multitask learning framework. So how do we enforce the invariance? So we want to say that the transformation invariance through instant classification. So we want to incorporate an invariant head, and we want to leverage a contrasted loss for the instance classification, and differently transformed versions should be mapped together, should be mapped to the same feature vector. Okay. Also, it's a standard that you want to use the memory bank or negative samples, because you want to have many more negative samples, and that always helps. That's what we are going to use. So the way we are going to enforce invariance is very simple. That we have the different samples. For each sample, we are going to do the augmentation, different transformation for each sample. So they will go to this network. This is what we are going to learn, F theta, which is a feature extraction. And this is MLP head, which will do the classification or learning. So what we will have, that we will want to do the contrastive learning. We want to say that while we look at the reference sample and a different transform version of that, and we will have m different transformations of that, and then we want to say that the transform version and the reference version should be similar, and it should be different. The negative samples should be different. The standard contrasted loss. So that way we want to learn these features to impose this invariance, which is kind of standard. Now,
sorry,
yes.
interrupt.
Excuse me?
Can you go back to the previous slide?
Yes.
Here, I have one question about the T1, TM. Are they similar or they can be totally different?
Which one?
The transformer, the tau 1, tau m, and tau m. The
this
most
one?
left. No, on the picture, the different transforms.
Yes, yeah. Okay. So you have the each image. That's like this sample example, on which we are going to do m different transformation. It's the same image, rotate, translate, scale, and so on. So the m different version of one sample. Then another sample, the m different version. Okay. So that's why we have the summation for m's go to 0 to m minus 1. So these are the same image being transformed, rotated, and so on. And we are going to do that for every sample. Okay.
Another problem is that here on the right side, the negative samples. How do you choose the negative samples from the memory bank?
Yeah. So if this is the image, then all are positive. Every other image is negative. So that's the way it works. Okay.
Okay. Thank you.
Okay. So the equivalence we are going to enforce, that we want to say that these transformation classified, classification should incorporate equivalent head and does not require any manual supervision. And we are going to create these proxy labels for different transformations. Okay. And it will ensure that these embedding retain the transformation equivalent features. So here's a network. So again, we want to learn this F theta, the feature extractor. Now, this is the different transform version of same image. Again, the M version, M transformation. Now here, we want to say that the network should say, because we have M-way classification. So this is the transform version 1, this is transform version 2, and so on. And for that, we are going to use simple softmax cross entropy. So this is the equivalence. Okay, so again, we are using all the transformation, but very differently. Here we want to say which transformation it is. So we will have, labels, say transformation 1, 2, 3, like that. So these will be our classes. So that way, now we have the equivalence and we have the invariance, and we explain how to do it. Now we are going to add the whatever number of examples which are known, few shots. So this will be the supervised learning for cross entropy. So we'll have these 3 heads, okay? And using all those, we are going to learn this beta feature extraction. So this is up to equivalence, invariance, and also the supervised head for few shot, 5 example or 1 example. Now, on the top of it, we are going to add the distillation. So what distillation will do, that will help us even better learn better representation. So this will be smooth prediction from teacher to encode interlabel dependencies, and also it will ensure the transfer of learned invariant and equivalent representation. So we are going to use the KL divergence between output of supervised classifier head, and also KL divergence for the output of equivalent head, because both are distribution, and then L2 loss between the invariant head, because that's not a distribution, it's just minimizing a loss. So this is the way it will work. So these are our formulas for this is for the supervised part, the head, and this is for the equivalence, and this is for the invariance. That's why we have L2. So, and when you put together this, it will look like that, okay? And as you see that we have these, for distillation, we have these losses, and when you combine all, we will have this loss to minimize to learn these features, okay? So again, this one is the cross entropy for the label data, very few shot. And this one is, we have here the equivalent, invariant, and the knowledge distillation. So we'll explain. Okay, so this works very well. So these are the results for the 5A C4FS dataset. There are several methods. So we are the best, the second best, and same thing for 5 shot. And these are results on FC100. Again, we have the best results. Then we can also do mini ImageNet. Now, mini ImageNet has many methods, and that's why we have second column. And this is, again, we do very good. This is second best. Then we can do tiered ImageNet, and these are the results. Again, we have the best results. This is second best. So the most difficult data set is meta data set, and this is about 10 different data sets they have combined. And again, we do the best here. And we have the red one, the top one, and the blue one is the second top. And you can look at the average. As you see, we do better, and most of these we do better also. So we did the ablation study also, as we talk about that, we can do simple baseline, baseline training, which means only label data. We can use only invariance. We can use only equivalence. We can use both combined, but no knowledge distillation. We can do just supervised and knowledge distillation, no equivalence and invariance, our full model. And these are the results for that. As you see that we can gradually improve the results, and this is give us the best one shot or 5 shot. Because few shot, you just have 1 example, or you have 5 example, which is pretty challenging. And the same phenomena for this data set and this data set. So now other thing is that affine transformation we talk about, there can be several possible transformations, right? So one is we can have the aspect ratio. So we can have 3 different values of aspect ratio. This gives you 3 parameters. We can have rotation for rotation. We can combine rotation and scaling. That gives you 8 parameters, 2 scaling, 4 rotation. We can take the rotation, aspect ratio, rotation, combined, give you 12 parameters. Or we can do this thing, aspect ratio, rotation, one set, then union of that, rotation and scaling, which, that one. Or we can do more combination and all kinds of things. So these are the number of parameters which we need to, number of possible transformation M, as I told you, that we do each sample, we apply all these transformations. So we did this evaluation and we found out that if we picked this combination, the 16, that works the best for us. And this was done on C4FS, and that's what we are going to use. Now, other way to look at is that we can take the full affine and quantize in different transformations, like look at rotation, different rotation and translation X, translation Y, scale, and all those things. We did that also. Now, if you take all that, that creates lots of transformations, 972. Now, it's not possible to apply each sample these many transformations. So what we did, we selected randomly 10 transformations and applied those to the images, and we did with that our experiment. And we found out that even that also works good, better using our original method. This is with the baseline. This is with only invariant invariant head. This is equivariant head, and this is combining, and this is with the 16, the previous one. So as you see that even with this sampling of the affine transformation, we can improve over the state of art. So also this representation we are getting is good. This is a Disney diagram of these 5 random test classes. So this is a baseline, which means this will just use the label images. And this will, if you use the baseline with invariance, and this with baseline with equivariance, and this is with combine. And as you see that these classes are well separated compared to these original one, or even if you use one at a time. So which is good. Now we also look at the other self-supervised losses. Okay, as you know, there are several other ones. For example, jigsaw or location prediction, context and rotation, so on. In all those, we can see that with our thing, we do relatively better than if you use each one of those, which is also good. So this also the code is available on this website, so you can download and work with that. So with that, we finished 2 pieces. This was few short learning. Yes, go ahead.
Yes, Professor Saha, could you please go to the slides of the equivalence? I'm not quite clear about this concept, so could you please explain?
Okay, so equivalent, yes.
Yes, thank you.
Equivalence is easy. So consider this, that I take image, not this one, okay. So I take an image, I apply a rotation of 30 degrees.
Mm-hmm.
Then I apply a rotation 60 degrees, then 90 degrees, then 120 degrees, okay? Mm-hmm. So there are 4 rotations. So I will say that the 30 degrees is one class, 60 degrees another class, 90 degrees third class, 120 degrees fourth class, okay? Wow. So I want the network to tell me when I do the testing that the 30 degrees, it should say class 1 is present. When I say 60 degrees, it should say class 2 is present. So that's the way equivalence work. So it is if I vary if I apply the transformation or vary, then the classification should equally vary. That's why it's called equivariant. If I vary, the output should vary also. So that's the way we do that. If network can predict this is 30 degrees, it will put in first class. If it is 60 degrees, it will put a second class. Then it is doing equivariance. Now invariance is different. Invariant is like opposite to that. If I apply 30 degrees, 60 degrees, it should always say it's a dog. Okay?
Mm-hmm.
It should not say it. So it's very interesting. So what my student Rizvi came up with, say, well, can you combine these? And he showed that, well, it works. Okay, is it clear now?
Yeah, so from the feature representation perspective, the equivalence can improve the feature discrimination ability or what?
Yeah, so it gives you the transformation power that these feature, it is the transfer learning that, see, you are learning now, the network is able to transfer that. You say, well, if it's 30, it's able to distinguish between 60. So the transfer learning capabilities, and that is always helpful. Okay?
Okay, thank you.
Yeah. Okay. So let's go now. Okay. So let's now talk about the third piece, and which is about the self-supervised learning. So now here we don't have any labels. So this is a work with my 3 graduate students, and this is under review, but it's available on archive. So one thing is that here we are going to do videos. So far we have talked about most of the work on the images. And so now the annotation for video is very costly compared to annotating images. By some estimate, if you take the connect is 400, then it will take about 28 years to watch. So many videos, it takes time and so on. This is just 400, now they have 700. So solution is that we want to do learning from unlabeled data. Okay. So now, as you know that the contrastive learning has been very popular in self-supervised learning for images, and it does as well as the supervised learning, which is very impressive. And it uses what is called instance contrastive loss. Okay, and a good example of that is Sinclair. So we have an image here, and then we apply the augmentation. We get this one, another augmentation here, and then we want to make these representation to agree because the same image. So it's basically similar to invariance we talk about. That is the instance contrastive loss Sinclair uses, and many other methods use it also for the images. Now, one can use that as it is for the video. And for video, it will happen that while we have video 1 and video 2, we take these 2 clips, clip 1, clip 2, and we do the 3D convolutional network to get the features. We have this, the MLP head, and then we get here representation. So this will become the anchor, and this is positive, that they should be similar because same video and should attract. And then we have another video, again 2 clips, you get the 3D CNN features, MLP, and this should repel. This should be different. They should be similar, they should be different. So this loss is like that we have the GI and GI prime should be similar, and then rest of them, other one, the red arrow should be dissimilar. So that is, and this is a cosine similarity as we have been talking about before. So that is insert contrastive loss for video and how we do it, and there are several methods which they have used. So now what our point is, that insert contrastive loss attracts all clips from the same video to similar representation. Okay, so it enforces a temporal invariance, and due to temporal invariance, this intercontrastal law does not gain from multiple clips, because the traditional in the video classification we use multiple clips because one video cannot fit in the GPU. So that's a problem. You can fit an image but not a video. So now here's an example that the problem is the nearest neighbor retrieval. Okay, so now if we solve this problem and look at the recall at top one, then if you keep adding number of clips, then if you use insert consortium loss, improve the performance doesn't change. But if what we are talking about, the tickler loss, then performance improve because we are looking at this diversity with respect to this representation. So therefore, our framework is that we want to encourage a temporal diversity at two temporal aggregations. One is the temporal pooling of feature map. So we want to pool it across features, and then we want to do clip level averaging, which pool it across clips. So for that, we introduced two new losses: local temporal contrasted loss. So this will discriminate between non-overlapping clips from the same clip. And global local temporal contrasted loss. This will discriminate between time steps of feature map of the input clips. Okay, so here is what we have. So we have a video. So we divide the video in 4 clips, which are shown here. Then we do the augmentation. This one set of augmentations, another augmentation. Then we get the features, 3D CNN, MLP, we get the presentation for each of these. Okay, so what we want to do, that this clip should be similar to this clip, and it should be dissimilar to the remaining clips in this, also remaining all clips here. So that is the local contrast loss, and it's contrasting clips from the same video. And the loss is defined here, that we say the GI and G prime I should be similar, and all these others should be dissimilar, which is shown here. So then we have global local loss, and in this we take one big clip, which we call global clip, and we find the CNN, 3D CNN features, and then we have to split these into these 4 pieces, 4 temporal pieces, slices, and then we apply the MLP and we get representative for each of the slice. Okay, and we do for those 4 clips in the same global crop, which is here, and we get the local representation for each of these as we did before. So now we have these representation from the global one, and they have represented from the local one. And what we do, we say that this and this should attract, and this and these should repel. And we do that also other way around, that this should attract this one. So therefore, it is enforcing temporal diversity at the feature level. As you see here, that we get the features, then we do the slices, and we are contrasting the feature level as compared to what we do local. So therefore, loss, now we have 2, because we do one direction this way, which is shown here, another direction other way, which is shown here. And of course, we have to do, this was just for one clip, clip. So we can do with all the clips, this clip, and therefore we will sum up these, and these are the losses. So then that's it, and it works very well, which is shocking, and reviewers don't believe that these results are true. So I'm trying to convince them to believe it. Yes, please.
Coming back to the previous slide, So in this double terms loss, there is one that is for the attraction, so between
Yeah.
Li1 and Gi1, and
Yes.
the other for the repel between Li1 and all of the others.
Yes.
Is it normal that they both have the same sign, or is it inside the H function that something changed?
Same. I didn't get.
I would expect a different sign, because if you want to, it's either you maximize you minimize the distance between Li1, Gi1, and then maximize it for the others. I mean, there should be an opposite effect, or no?
No, I mean, it's the same thing. We are comparing this way, or you're comparing this way. The same thing, right? Why should be different?
Okay.
Your H is defined, is right? I told you cosine of angle between two feature vector. It should be the same thing.
Okay, so H is a distance.
Yeah. That's the same thing I told
you. So in one case, you want it to be small, because you want two components to be close, and in the other, you want them to be far.
Yes, that's right.
Okay, so if it's the same distance, isn't okay, so it's maybe because the arguments are reversed in
it's very simple thing. Yeah.
Okay. Got it.
Yeah. Okay, so experiments. So so now we are going to first talk about the pre-training, self-supervised learning, and we are not going to use labels. And so we are going to use either UCF 101, or we are going to use the Kinectics 400 for the self-supervised learning with no labels, okay? And then we are going to use this different architectures, 3D Resonate, R2 plus 1D, and C3D. And now then for downstream tasks, we are going to do full fine tuning on downstream tasks for action recognition. And so that we'll do UCF 101, HMDB 51, and diving data set. And then we also do nearest neighbor retrieval. Downstream tasks would be no fine tuning, and fine tuning with limited labels, whether it's 1%, 10%, 20%, and so on. And then linear evaluation. Okay. And linear evaluation will only fine tune the final classifier layer. So results on action recognition. So here we go. So these are the different methods. And the interesting thing is all these methods are either last year or this year. So you can see this area is so active, so many methods, less than 2 years, and which is amazing. And this is the different configuration, like frames and resolution, because different methods use different configurations. So we want to list that. And now, so we are going to do the pre-training on one data set and then fine-tuning other data set. So this is pre-training in UCF 101 and fine-tuning on UCF 101 also. So as you see that we get a huge improvement, on this. This is second best. Here now pre-training UCF 101 and fine-tuning on HMDB 51, again we get a 5% improvement. Here the pre-training self-supervised learning and kinetics and fine-tuning UCF 101, again we get good improvement here. And this one is connected to HMDB, again we have 53 from 49 or something. So which is really good. And so these are the results on nearest neighbor retrieval. So these are the methods. And we go UCF 101 to HMDB. So it's a recall at 1. And we get pretty good improvement. And this is recall at 5, recall at 10, recall at 30. So that's, again, every case we get a huge improvement. So this one shows the qualitative results for nearest neighbor retrieval. So let's say query is this action, which is the head massage. Now, if you use the IC, you get these, the only instant contrasted loss. It gives you playing violin, playing cello 2, and playing violin 1. So it's wrong. Top 3 are wrong. But when we use our thing, so we get all 3 correct. Second, floor gymnastic. So we get 2 correct, 1 wrong, and here all are wrong. Only IC, insert contrast loss. This one, the haircut, and we get all correct. And this one is blow dry and haircut 1 wrong. So that's qualitative results. The other thing we can do is use the limited label. So let's say we use only 10% of the label for fine tuning or 50%. So we compare that with our method, which works pretty well compared to RotNet and MEM, DPC, and so on. So that also does pretty well here. Now we did also ablation. So remember that we are using 3 losses: the standard loss, IC, and these are 2 new losses. So we are comparing on top 1 classification on these different data sets and also the retrieval. So now if you use the random initialization, these are results that are pretty bad, which is understandable. So here, if we use our 2 losses, we get we get these performance which are better than random. Now, if we use IC, which works better, in these cases, and now when we combine IC with the local, we get 8% improvement here, 6% here, 11% here, 10% here. And when we do IC with the global local, 10%, 5%, 10%, which is good. Now, when we use all 3, we have 15, 11, 14, which is very nice. Okay. So now this data set, diving data set, is pretty interesting because it has these 3 main classes: takeoff, which is a dive groups; movements in flight, which is somersault and other twists; and entry, which is dive positions, different stages. So this is much more complex because this is a fine-grained classification. Two, otherwise, identical categories may only have fine-grained differences. They look the same, actually, you will see. And so it's limited only to 1 of the 3 stages. So these are actually, these are the 48 different classes. As you see that there are different branches, and the takeoff, somersault, twist, and then you can get all these different, they have 0, 1, 2, 3, all 48 of those. So, and these are the videos. Now these are all 3 different actions, but you as a human won't be able to see what exactly is different. Now in this one also we do very well. So as you see that, Connected give you 18, instant contrast 15, we do 22, about 7% improvement. So also, as I said, the main contribution of our work is that we want to bring in temporal diversity. And here, the nearest neighbor retrieval, as you see that when we add some more clips, then we improve significantly, and compared to only IC or some other methods, IC and local, global. This is same phenomena for the nearest neighbor retrieval, same phenomena for linear classification, which tells you that the number of clips per video, if you use more, it will help us. So now, other thing about this method is that we can distinguish visually similar classes. So here we picked the 9 classes, and this is a confusion matrix. As you see that some of these classes are being confused, like cricket shot and cricket bowling, okay, these 2. Then we have front claw and brace stroke, okay, they are also confused. Then we have playing piano and playing violin, they are confused here. And then we have pull-ups and jump back, it's confused here. So now when you use the IC only, in instant contrasted loss, that improves a little bit, but not as good compared to Tickler. Say, this is very nice. We get a very good confusion matrix, and which is amazing. So again, for this one, we have Disney's visualization, random initialization, you get this. Instant cosine helps a little bit, but here we get pretty good compared to these, it's all more combined, compact. So this was the temporal contrastive learning for video representation. And this finishes the 3 pieces. So I talk about the semi-supervised learning and the few shot learning and the self-supervised learning. So just to summarize, the semi-supervised learning, we use what we call uncertainty aware pseudo-labeling, and it's a very simple, efficient framework for effective pseudo-labeling based method. It gets the SOTA, state of art results, compared to consensus regularization based method. That's what we fill the gap, and people should start using pseudo-labeling. And it does not rely on any strong augmentation. And we are the first one to propose negative pseudo-labeling for self-supervised learning, semi-supervised learning. And UPS is versatile. It's domain agnostic. I showed you results on actions. I showed you results on the Pascal. And that's why it works for multi-label classification. Now, few shot learning, we use the very, different kind of opposing criteria of invariant and equivariant representation simultaneously enforce. To learn the representation, it leads to better class discrimination and better transfer features and simple implementation, no excessive architecture changes, and transformation discrimination for equivalence, invariance, instant discrimination for invariance, and we introduce multi-head distillation, leads to further improvement and outperform all other few shot learning methods. And we show the result on 5 popular benchmark data sets, which is a lot of computation, a lot of experiments. Then self-supervised learning, I introduced temporal contrastive learning, Tickler. And the main point here is that we want to introduce temporal diversity on top of standard instant contrastive learning and propose 2 new classes, local temporal contrastive and global local temporal contrastive. And we get the state-of-art performance on video understanding task. So this is end of the talk. Besides this, we have a lot of other work going on. So these are the 6 papers we had in CVPR last month. And besides this equivariance and invariance, which is this one, we had a paper on the action dependency, temporal action localization. We had paper on detecting drones from drone videos, which is pretty interesting new area. We also have paper on the grounding of question answering task, and we had a paper on out of distribution using one-dimensional subspaces, and then we have another self-supervised learning method for anomaly detection. So beside me, at our Center for Research in Computer Vision, we have 3 other faculty, and actually Dr. Chen is here attending the talk, and we have Dr. Rogesh Rawat and Dr. Mahalan Abbas, and we have a very large group. So we have several associate faculty who are working in different departments, like medical, physics, and mathematics, and so on. And also we have 2 postdocs, and we also have the master's program in computer vision, which we are starting this fall. This is the first public university in the US offering the math.
Thank you. Thank you.